Homework 5, problem 1. Find the electric potential, V, between the parallel plates. In this situation here, we're on the edge. We've got a strip, half of the strip at y equals 0 on the xz plane. Half of the strip is at a positive V naught potential, and half of the strip is at a minus V naught potential. So in order to do this problem, we're going to use separation of variables. In order to properly write out the separation of variables, we need to explicitly write down the boundary condition and the problem as a whole. So the problem is simply the Laplace's equation, minus del squared V is equal to 0. One of the conditions that we're going to have is this is independent of the x coordinate. So we're going to be able to write that V is simply a function of only y and z, and we're going to make that assumption of separation of variables, right, that this is a product x, y of y. Now for the boundary conditions, we're going to have that V at z equals 0 must equal V where the separation between the plates we'll label as A, 0. So we have the potential is 0 on the top and bottom. The potential as y goes to infinity, so the limit as y goes to infinity of V of r must be 0. So we have to have a finite zero potential as we go off to infinity. And the final boundary condition is that at y equals 0, we have a piecewise function. We have minus V naught if z is greater than a over 2, and we have positive V naught if z is less than a over 2. And that uniquely describes the problem. Now I've already told you the method that we're going to use. We're going to use the method of separation of variables. Whenever we make this assumption that V is a product of x and y and we plug it into the Laplace equation, we're always going to get these two equations out. We're going to get that the second derivative of capital X is some constant, which I'm going to label Cx, times capital X itself. We're going to get that the second derivative with respect to y, capital Y, is a constant, I'm going to call Cy. Oh, why did I have this x and y? This should be, of course, y and z. So that's going to go away. Sorry. Cy times y is a function of y, and then d over dz squared, z equal to cz. The other condition that we're going to have, of course, is that cy plus cz must equal to 0. Now, we know that the solution to these equations, the second derivative of a function is equal to a constant times a function, are either exponentials if this constant is positive, or their sines and cosines if the constant is negative. In the z direction, I have 0 on top and bottom. The only solution with exponentials at 0 on top and bottom is 0 everywhere, which is uninteresting. So for the z direction, where I go from z equals 0 to z equals a, if I want interesting stuff between 0 and a, I need sines and cosines. The way I do that is by setting cz less than 0. And so here, because we want a non-zero z, I'm going to let cz be less than 0. That means we're going to define cz to be equal to minus k squared, sorry, where k now can be any number, right? But the square of a number is always positive, so minus square of a number is always negative. And by this thing here, cy is going to then be positive k squared, where this is the same k. Moving on, we are then going to want to solve the differential equation. The differential equation in the z direction is right here, and so rewriting that, that's d over d z squared, capital Z of little z, is equal to now minus k squared, capital Z, little z. The general solution to this is a linear combination of sine of kz and cosine of kz. Now we know, of course, we're going to next apply a boundary condition. So the boundary condition we have is that v r at z equals 0 must equal to 0. For us, that's going to translate to y times z, but we have z. Z at z equals 0, the a is going to go away because sine of 0 is 0, so the b is going to give cosine of 0 is 1, so it's just going to be b. And so this is going to give y of whatever y is times the constant b must be equal to 0. So if we have some interesting thing in y that's not always equal to 0, then b must be 0. And this is the conclusion that we're going to have. B must be 0. The boundary condition v of r at z equals to a is equal to 0 is going to translate into, now we know that b is 0, so now we still have a left over. So this is going to be y capital A times sine of k a must equal to 0. This is only true when sine of ka is equal to 0, so this is going to give us a condition that ka must equal n pi for n equal 1, 2, 3, dot. Now again, I said that k could be positive or negative, but it's a little bit of a lie, right? Because if I have n equals -1, that's the same as n equals 1, so there's no difference between those. So I specify everything simply by looking at the positive ends here. So from this, we're going to get, of course, the condition that k is n pi over a. And so that tells us now, right, that z, I guess, can be this a times sine of n pi over a times z. Okay. Now we're going to look at the y differential equation. Okay. So the y differential equation, when we look at it here, is we're going to recopy it, but remember that our cy is a positive k squared. So when we copy that down, we're going to get that the second derivative with respect to y of capital Y of y is equal, now we have n pi over a quantity squared, capital Y of y. The general solution to this is going to be that this is a linear combination of positive and negative exponentials, of growing and dying exponentials. For the growing exponential, we're going to get m pi over a y, and then for the dying exponential, we're going to get minus n pi over a y. Now we're going to look at the boundary conditions. The first boundary condition that we're going to look at is this one, the fact that as y goes to infinity, the VR must go to 0, and v is, of course, a product of y and z. And so the limit y goes to infinity of v of r is going to be whatever z is, we're not going to worry about plugging it in explicitly right now, times the limit as y goes to infinity of this d e to the n pi over a y plus e to the minus n pi over a y. And that must equal to 0. Well, we can see straight off the bat that in the limit as y goes to infinity, this term here goes to 0, so we're going to ignore it. This term here blows up, so if this needs to equal 0, my constant d must equal 0. Okay. So now I'm going to combine what I have again. I'm going to combine what I know about y. My y of y needs to now be a capital capital E exponential of minus n pi over a y. Okay. And combining now so using this statement that the potential I'm looking for is the product of this y and z, I'm going to be able to write that v, function of y and z, is going to be equal to, I'm going to leave some space because I know something. I have a constant a and a constant e, but I don't, when they're multiplied together, I can just absorb the e into the a. So I'm going to write this capital A, and then exponential of minus n pi over a y times the sine of n pi over a z. Now, the other thing I would like to point out at this point is that this is true for any possible n. These functions, some constant exponential of minus n pi over a y times the sine of n pi over a z, is a solution to Laplace's equation, which is just off the screen, to Laplace's equation, that also satisfies these first three boundary conditions, okay? And that's true for every n. And so, because of the superposition principle, a general solution then needs to be a sum over all of the n's. Okay? And so this is the situation we have now. So this is what our potential looks like at this point. At this point, we want to introduce the final boundary condition. Okay. The final boundary condition is this one right here, that the potential at y equals 0 has to equal this piecewise function. So keeping that there, I'm going to rewrite this. So the final boundary condition is that v at 0 z, which is going to be equal to, at y equals 0, that's just leaving that off, so the sum n of an, the exponential of 0 is just 1, so that's 1 times the sine of n pi over a z. And this must equal the piecewise function that we had before. We're at minus v naught for z greater than a over 2, and we're at plus v naught for z less than a over 2. And so now here we have a situation where the desire is to find these coefficients a sub n such that when I add together this sum, I get this piecewise constant function. A sum like this is known as a Fourier series. It turns out that you can make any piecewise continuous function out of a Fourier series. So we're going to go ahead and do that, any piecewise bounded continuous function. And the trick that we use is called Fourier's trick. And so what we're going to do is on both sides, we're going to multiply by sine of m pi over a z. And we're going to integrate from 0 to a on z. And we're going to do that on the left-hand side here and on the right-hand side there. So go ahead and starting that out, we're going to get the sum from n a n. We're going to have an integral dz from 0 to a. I get my sine of n pi over a z. Then I'm going to get a sine of m pi over a z. That's the left-hand side. On the right-hand side, I'm going to break my integral into two pieces. Okay, so I'm going to get v naught, and then integrate from 0 to a over 2 dz, and I still have to multiply by sine of m pi over a z. Then minus, because I factored out the v naught, but I haven't factored out the minus from there, from a over 2 to a sine of m pi over a z. Now, at this point, the power of the Fourier trick is in what we call the orthogonality of these sine functions. So the orthogonality of the sine functions is the following statement. Okay? The integral from 0 to a dz sine n pi over a z sine of m pi over a z is going to be equal to 0 if n is not equal to m, and if n equals m, this is just sine squared. The integral of sine squared is half whatever range you're integrating over, as long as you integrate over some half integer of the period. And so this is a over 2, since our range is 0 to a, if n equals to m. So that makes the evaluation of the left-hand side really simple. For all of the terms in this n sum where n does not equal m, we're going to get 0 from there. And for the one term where n equals m, we're going to get am times a over 2. So on the left-hand side, we're going to get am times a over 2. And that is equal to, on this side, we're going to have our v naught. We're going to have a minus, a over m pi, and this, then the integral of sine is, the integral of sine kx, right, is 1 over k, minus 1 over k cosine. So that's the minus 1 over k. And then we're going to get cosine. And so we're going to get cosine of m pi over a z evaluated at 0 and a over 2 minus the cosine of m pi over a z evaluated at a over 2 and a. Just continuing the algebra, cosine of 0 is 1 cosine of, this is cosine of m pi over 2. I'm going to get a positive cosine of m pi over 2 from this one. I'm going to get a positive cosine of m pi over 2 from that one. I'm going to get a negative cosine of m pi and a negative 1, and a negative here. So I'm going to write this out. So this is am. I'm going to multiply by a over 2 as well, will be 2 v naught over m pi, keep the minus sign, and here I'm going to get, let's see, so this is the minus 1 from here, and then I'm going to get 2 cosine of m pi over 2, and then minus cosine of m pi. Okay, I distribute the minus, so this will be plus 1 minus 2 plus cosine. And now I can go through and I can look at a few of these for looking just at the underlined case here, this under bracketed. For m equal to 1, I have 1 minus cosine of pi over 2 is 0, so 1 minus 0, and then plus cosine of pi is minus 1, so plus 1 plus minus 1 is 0, and so this thing is going to give me 0, so the bracket gives 0. For m equals 2, you can get 1 minus cosine, now this will be cosine of pi. Cosine of pi is minus 1, so 1 minus 2 times minus 1, so 1 plus 2. and cosine of 2 pi is positive 1. So 1 plus 2 plus 1 is 4. So my bracket gives 4. For m equals 3, we're going to have cosine of 3 pi over 2 is 0. Cosine of 3 pi is negative 1. So 1 plus 0 plus negative 1 is 0. So my bracket gives 0. For m equals 4, we're going to have cosine of 2 pi. So cosine of 2 pi is positive 1, and cosine of 4 pi is positive 1. So 1 minus 2 plus 1 is 0. So that bracket is going to give 0. And it turns out that this is just going to go again. So this will also be for 5, 6, 7, 8. And we're going to repeat this pattern in loops of 4 here. Okay? So, combining everything together, going back to my expression for what this, oops, not even that one. Here we go, for my expression of what v is, I'm going to finally write that v of y of z is equal to, so I'm going to combine this 4 to that 2 and make 8. So I'm going to have a sum, and my n is only going to go 2, 6, 10, dot, dot, dot. And so it'll skip every 4. Then I'm going to get 8 v naught over n pi, then multiplied by e to the minus n pi over a y times sine of n pi over a z. And that is the potential between those two plates.